Hello Internet, welcome to another tutorial in information theory and coding. In today's tutorial, we'll discuss linear block codes in detail. We'll discuss linear block codes with a sample numerical also. So let us begin. Now, in a communication system, we have a transmitter which has the job of transmitting code. So if it receives a message signal, for example, our message signal is a 3-bit message signal and it is 110, then one block of this transmitter section is the block code generator. Now the task of this block code generator is to generate a code word out of this message and transmit it via the antenna or over the wire, whatever the model is. So in other words, this code word is generated by this block code generator, which consists of message plus parity. Now, why is this parity important? Why do we need the code word in first place? It's because of the reason that whenever this code word is received at the receiver section, we'll be able to see if an error is there in the message, and if there is an error, we'll be able to rectify it. So with the help of this additional parity bits, we'll be able to retrieve the information of the correctness of the message. So we'll get this code word, received code word here, and this will be the block code decoder. So it'll give us the message again after correcting it if it has an error. So that is how the general block diagram of the communication system in information theory and coding will look like. Now what happens is, for a certain amount of bits in the message, we assign certain amount of code words, and that would actually depend upon how much overhead do we want to spend on a message signal. For example, if we look at this question, it will be more clearer. It says for a 6,3 code, the generator matrix is, of course the generator matrix will be here, which will generate the code word, will generate the code word from the message using this generator message. But now the fact of the matter is that if you look at this information given in the question, you'll find the values of n and k here. Now in every question you'll find the value of n and k, where n is the code word length and k will be the message bit length. So the first thing is 6. So in other words, code word will be 6-bit long, and out of those 6 bits, 3 bits will be assigned to the message. So we are left with the parity bits. Let us say parity is denoted by B. So parity bit is given by of course 6 minus 3, or n minus k is equivalent to 3. So in this particular case, we get our parity also of 3-bit for a 3-bit message. If you get a 7,3 or 7,4, then that's how you can find out the number of parity bits, n minus k. So this is going to be the first thing. Now if you look at the generator matrix, the generator matrix will consist of an identity matrix and the parity coefficient matrix. So this will be the format of the generator matrix, and we'll be concerned about this portion of the generator matrix because in order to find the parity, which is going to be B in our case, it is going to be M message into this parity matrix. The parity associated with any message can be found out using this formula, M into this portion of the matrix. So first things first, we'll start this question so that we basically start to understand how the flow of the question goes. So the first part says you need to find all corresponding code vectors. Before we can find the code vectors, we need to understand how many messages do we have. So for a message bit length of 3, which will be M0, M1, M2. So 3-bit message means it has 3 bits which are given by M0, M1, M2. We can have possibly 8 different messages ranging from 0, 0, 0 to 1, 1, 1. So we could possibly have these many messages, and we need to find out the code words for each of these messages. This is what the first question says. All corresponding code vectors, and we know that the total code will be message plus parity. So it will be M0, M1, M2 and B0, B1, B2. So we know that our parity is also 3 bits, so I'll say B0, B1, B2 are my parity bits. So next thing is finding the parity bits. What I'll do is I'll assign B0, B1, B2 here also, and this whole combination will be my code word. So this entire thing will be my code word joined. Now how do you find the parity bits? For that the formula is pretty simple. So putting B0, B1, B2, and instead of M I'll say M0, M1, M2 multiplied by this matrix. So this is going to be 1 0 1 0 1 1 1 1 0. And when we multiply this row with this column to get our first element, please understand that we are going to use the XOR operation. For example, B0 will become M0 into 1 XOR M1 into 0 XOR M2 into 1. So in short it will be M0 XOR M2, and similarly B1 will become M1 XOR M2, and B2 will become M0 and XOR M1. Now with the relationship that we have gotten between the parity bits and the message bits, we can draw its block code generator diagram. So the encoder for the block code would look something like this. So it will have these 3 bits, M0, M1, M2, and this encoder will generate B0, B1 and B2. So it will generate so by XORing some things. We know that B0 is generated when M0 and M2 are given to it. B1 is M1 and M2. B2 is M0 and M1. So this becomes our encoder for the block code generator, which is placed here. Now we have the task of finding the B0, B1, B2 for each of these code words. So that is pretty simple. By substituting the values of M0, M1, M2, we can find B0, B1, B2. For example, the first code word will become M0, M2 XORed will give me a 0, 0 and a 0, because M1, M2 is also 0. Now next is B0 is M0, M2. M0, M2 XORed gives me 1. M1, M2 gives me a 1. M0, M1 gives me a 0. Similarly, 0, 1, 0 gives me 0 and 2. 0 and 0 will be 0. 1, 2 will give me a 1. And 0, 1 will give me a 1. And 2 give me a 1. 1, 2 give me a 0. 0, 1 give me a 1. 1, 0, 0, 1, 0 give me a 1. 1, 2 give me a 0 and 0 and 1 give me a 1. Alright, now that is how you can find the code word of substituted the values of B0, B1, B2. The entire code word that will be transmitted will be 0, 0, 0, 0, 0, 0, which is a 6-bit code word. Now the next thing is to find the weight of each of these code words. So how do you find weight? Weight will be the number of ones in each code. So if you have no ones in the code, then leave it blank or put a dash, and we have 3 ones here and 3 ones here, 4 ones, 3, 4, 4 and 3. So the number of ones will determine weight, and the minimum number of ones in this column would determine d min, and this is known as the Hamming distance, or at times it's also known as Hamming distance. So very important property, but easy to find out. Now why is it important to find out the d min or the Hamming distance? Because two of the other quantities, number of errors detectable, depend upon this, because number of errors detectable is specified by S. Now this is given by basically S less than equivalent to d min minus 1, because it's derived from d min should be greater than equivalent to S plus 1, and this is going to be the first part that we can find out from d min. The next thing that we can find out is number of errors that we can correct and that is given by t. So that has a formula: d min should be greater than or equal to twice t plus 1. So very important quantities that we have found here: d min, s, and of course t will become less than or equal to d min minus 1 upon 2. So t again, very important. Now if you look at the we found the minimum distance, by the way, and the third question says verify that this code is single error correcting code. If we put d min is equivalent to 3 here, so it will give me s becomes less than equivalent to 2 and t becomes less than equivalent to 1, substituting d min here as 3. So we can detect 2 errors and we can correct 1 error. Right? Now the next part is to find the parity check matrix. Parity check matrix is found very easily by taking the transpose of this matrix here, and this is a part of the generator matrix. It's given by P. So parity check matrix is given by H, and it is nothing but I unit vector with transpose of this P, and transpose of this matrix will become, these rows will change into columns and so on. So this will become, if we were to find H, this will become 1 0 0 0 1 0 0 0 1 1 0 1 0 1 1 1 1 0. So this becomes our parity check matrix. Super easy to find. Now, what is the importance of parity check matrix? We'll see that. Now the next question is to determine transmitted code word if received code word is this. So the next term that I'm going to introduce is syndrome. Syndrome is kind of a detection technique where the error is, and it is given by S is equivalent to R into H transpose. Now we need to find out syndrome. Syndrome will tell us where the error lies, and if we have received a code word 100011, and if we multiply it with the transpose of this vector, which will be 1 0 0 0 0 0 1 1 0 1. So this is going to be the transpose of, so we need to find out S. So S is going to be again a 3-element quantity. So let's find that, and while we multiply the row with the columns to find that, please make sure this is an XOR operation. So this is 1, and next 3 are zeros, and then we have a 0 and a 1, and 1 XOR 1 is 0. Then we have 0, this goes, and 1 and 1 XOR 1 is 0 again. Then we have this goes away, next 3 go away. Then we have 1 and 1 XOR 0 is 1. So we've got our syndrome to be equivalent to 0, 0, 1. Now we need to see this syndrome in the H transpose matrix. Where do we find 0, 0, 1 in the H transpose matrix? We'll surely find this syndrome in H transpose matrix. If syndrome is 0, then there is no error. However, if syndrome is non-zero, then we need to find out where the exact match is found. So 0, 0, 1 is here. So it is third row from the top. So the third received bit is erroneous. And what could be the error in a digital or a binary signal? This must be 1. So the actual code word should have been 101011. So this was the correct code word which was transmitted. Of course, some error came in that changed this 1 to 0. So that is how you find the error. And if you were to find it from the least significant bit side, then you can see that this is 0, 1, 2, 3/4 from the bottom. So the 4th bit from the right side is erroneous, and that is how syndrome is found to check the error for the received code word. And that is about it in linear block codes. More or less everything is covered in this topic, which can be asked in a question of a linear block code. We have covered the code length, the message length, the length of the parity bit, generator matrix, how to find a code word, how to find weights, how to find number of errors detectable, how to find number of errors correctable, and we have drawn the encoder for the block code, and how to find the parity check matrix, and finally how to find error in the received code word using syndrome. And I hope this informative tutorial, comprehensive tutorial was of help. And if you like the contents, give it a thumbs up, consider subscribing to the channel. That will be a great help. I'll see you in the next video. Take care. Bye bye.